All right, and welcome back. So today we are going to be talking about exponential functions. You might have heard things increasing exponentially or decreasing exponentially, and today we're going to be discussing what that actually means. We're going to be going through some characteristics of exponential functions as well as how to determine whether a given table is going to be a linear function or an exponential function. So again, today the essential question is, what are some of the characteristics of the graph of an exponential function? So here's the key concept. Exponential functions are of the form y is equal to a times b raised to the xth power, where a is not 0, and it should make sense that a can't be 0, because 0 times anything is 0. So we wouldn't have a function, it would just be y is equal to 0. Right? We just have y is equal to 0. B cannot be 1, because we know that 1 raised to any power is going to be 1. So we wouldn't have a function, it would just be y is equal to a. And then b has to be bigger than 0. Okay, so those are the three main parts of an exponential function. Now, a key component is that the x power is only attached to b. We call b our base. So we can sometimes see this written as y is equal to a times b to the x. Okay, again, the xth power is only attached to our b value. So let's show this in a couple of different examples. So in this problem, it says copy and complete each table for the exponential function y is equal to 16 times 2 to the x. In each table, what do you notice about the values of x and what do you notice about the values of y? Please pause the video, try and fill in the table as best as you can, and then resume when you're ready to move forward. All right, and poof, look at that. All of the values have been inputted for you. So let's look at the table on the left-hand side. What do you notice about our x values? Well, they're increasing by 1. And what happens to the corresponding y values? Well, those seem to be doubling. 16 times 2 is 32. 32 times 2 is 64. So on and so forth. All of these values, when our x was increasing by 1, the values were doubling for our y. Let's look over on the right-hand side of the table, or the table on the right-hand side, I should say. Notice our x values are increasing by 2. What is happening with our y values? Well, we go from 16 to 64. We're multiplying it by 4. 64 to 256. Multiply by 4. And this pattern happens all the time. As our x values doubled, our y values quadrupled, right? Great job, cool, sweet, awesome. Here we go. So now in this example, we're going to say, okay, does each table represent a linear or an exponential function? And please explain. So within this topic, we want to first look at our x values. Are those increasing at a constant rate? For a, we have 0, 1, 2, and 3. So yes, those are increasing at a constant rate. They're increasing by 1. Perfect, sweet. Now for our y values, we have two possible instances. When 2 goes to 4, we're adding 2, or we're multiplying by 2. When 4 goes to 6, looks like we're adding 2, or we're technically multiplying by 6 over 4. Which one of these match up? Is it when we add or subtract, or when we multiply or divide? It's going to be when we're adding and subtracting. So we're actually increasing by 2. So since we're increasing in an addition or a subtraction point of view, this is going to be a linear function. And we could put this into slope-intercept form because I know you can. Let's look over on the right-hand side though. So we have our x values look to be increasing by 1. Perfect, sweet. But now let's look at our y values. Well, we go from 4 to 8, so we're adding 4, or we're multiplying by 2. For 8 to 16, we're adding 8, or again, we're multiplying by 2. So which pattern is matching up? Adding 4 and adding 8? No way, Jose. We're multiplying by 2. So since we're doubling our values, this is going to be an exponential function. So over on the left, we have a linear function, and over on the right, we have an exponential function. But these aren't going to be the only questions that we are going to be asked. We're also going to be asked to evaluate each function for the given value of x. And all that means is wherever we see an x, we are going to input the given value. So for a, we have y is equal to -2 times 5 to the x. And we want to find out the value of y when x is 3. So all we do is input 3 for x. So we're going to have y is equal to -2 times 5 to the third power. 5 to the third power means 5 times 5 times 5, which we get 125. Now we do -2 times 125, and we get -250. That's all. Nice job, folks. Nice job. Now over on the right-hand side, we have y is equal to 3 times 0.5 raised to the x power, and we want to see the value of y when x is equal to -2. So there's two ways that we can go about this, and I'm going to show you both. One, we can work with decimals, or we can work with fractions. So I'm going to separate this page in half. So let's work with the given as a decimal. So all we're going to do is replace the x with -2. So we have y is equal to 3 times 0.5 raised to the -2nd power. We get y is equal to 3 times 12. Can use a calculator for that. And then, oh, I'm sorry, I lied. I got ahead of myself. Sorry. We get is equal to 4. There we go. And then 3 times 4, we get 12. So y is going to be 12. But what if we wanted to work with fractions and use our exponent properties? So we can actually rewrite this. Y is equal to 3 times 1/2 as a fraction to the -2nd. We can use our exponent properties here. We get y is equal now to 2 raised to the 2nd power. When I have a negative exponent, I have to take the reciprocal of it. So now it was 1/2 raised to the -2nd. We flip that and we get a positive exponent. So now look at that. We still get the same value. 2 squared is 4. And y is going to be equal to 12. And that should match up. And it does. Sweet. Nice job, folks. So it's 6 to 1, half a dozen the other. Sometimes it's going to be easier to work with fractions because we're going to get exact values. And as you see, these numbers can get very big or very small very quickly. So sometimes it's better to work with fractions. I personally like fractions better than decimals. I have heard a phrase, fractions are our friends, decimals are the devil. You can use that if you want to, but I like fractions because they are exact. Decimals, sometimes we round and they're never-ending decimals, but fractions are perfect, okay? They are exact values. So 6 to 1, half a dozen the other, but again, personally, I really enjoy using fractions whenever I can because I can get an exact answer. So here are some problems for you to try out. Please pause the video, attempt these 4, and then resume when you want to see the answers. All right, so here are the answers. Want to add in something real quick for 4. When x is 0, y is 1.5, or 3/2. All right, folks, good job so far. Nice job. Here we go. So here's another core concept for you. When we're graphing, we have technically 4 instances. Over on the left-hand side over here, when b is greater than 1, we have 2 possible graphs. The blue graph shows when a is greater than 0. Notice how you start out close to the x-axis when our x values are negative. And then once our x values get positive, boom, we just go and increase at the exponential rate. Likewise, when a is less than 0, so it's a negative number, again, we're going to be starting close to that x-axis, but we never cross over the x-axis. And then as our x values increase, we then grow exponentially, and we have that curve, okay? Over on the right-hand side, this is different because now we're talking about when b is between 0 and 1. Remember, b cannot be 0 and b cannot be 1. So this is another set where b is going to be somewhere between them, right? B could be 1/2, could be 1/4, whatever, right? But it's going to be between 0 and 1. So looking at the blue graph shows when our a value is positive. We start out really, really big, and then as our x values increase, we get very, very close to that x-axis, right? We get very close to the x-axis. And likewise, in the red, when our a value is negative, we start out very small, and then we get extremely close to that x-axis as our x values increase. But again, we never cross over the x-axis. Never cross over the x-axis. Oh man, we never cross over. Okay, they get very, very close to it, but they never actually cross over. And let's show that in another example. So in this example, it says graph f of x is equal to 4 times 2 raised to the x power. Compare the graph to the graph of what's called a parent function. Describe the domain and range of f. You also might hear this as the mother function. You might hear it as a parent function or the mother function. First, let's graph f of x is equal to 4 times 2 raised to the x power. So please, I always like to fill out a table. I like to use the values of -2, -1, 0, and 1. That way I have some negative, I have 0, and I have at least one positive number. So please try and fill out this table, and then let's then graph it. So when I fill out this table, when x is -2, I get 1. When x is -1, I get 2. When x is 0, I get 4. And when x is 1, I get 8. And notice that they're increasing by 2, right? We're increasing by 2. That should make sense because our base is going to be 2. So let's actually graph it. -2, 1, -1, 2, 0, 4, 1, and 8. So it looks something like this. And notice again, I'm not crossing over that x-axis. Now, the parent function or the mother function is just the given function without an a value. So it's going to be f of x is equal to 2 raised to the x power. And when we graph that, if I use 0, I get, if I use 0, I get 1. If I use 1, I get 2. If I use 2, I get 4. If I use 3, I get 8, 1/2, 1/4. So notice here that it seems to be just a little shift from the parent function. We moved left just a little bit, but it's the same curvature, okay? They never cross over the x-axis, but it looks like it just was shifted left, right? Now let's talk about the domain and range. So the domain is all the possible x values. Well, it's all real numbers. You can input any x value you want. Now our range, since I'm on top of the x-axis, we never cross over. Y is always going to be greater than 0. That's our range. Okay, it's any y value greater than 0. If this graph was flipped and it was underneath the y-axis, then it would be all y values less than 0. And that's how we graph an exponential function and compare it to the parent function. Great job, folks. If you have questions, please feel free to reach out.